Hi, my name is Zachary Lyons, and today I'll be presenting the Physics 2212 Lab number 5 at Georgia Tech, Magnetic Braking with Faraday Lab. The goals of this lab were to collect data from observing a bar magnet falling through a conductive tube of aluminum foil, and then to model that falling magnet computationally in VPython. We're going to compare the computational model from that to the observed data that we got from dropping the magnet. The findings were that the average time for the magnet to fall through the tube was 0.978 seconds, with a magnetic dipole of 7.91091 AM squared. The predicted time from the computational model with this magnetic dipole is 1.033 seconds, and the magnetic dipole of 7.681091 AM squared. The predicted time matched the observed time in the computational model. Some key concepts for this lab are Faraday's law, which relates the integral of the dot product between an induced electric field and the length of the outer edge of an enclosed area to the negative derivative of the magnetic flux, where the magnetic flux is equal to the dot product between the magnetic field and the area where the magnetic field flows through. In this lab, the first equation is used to find the magnetic flux. The electric field produced by the change in magnetic flux follows the loop and is in the same direction as the current. The magnetic force on a wire loop is equivalent to the cross product of a current multiplied by the L vector with the magnetic field, where the L vector has a magnitude equal to the length of the wire. The following equation is derived for the force on the loop. Using Newton's third law, we can assume that the magnitude of the magnetic force on the loop is equal to the magnitude of the force on the magnet by the loop in the opposite direction. Using Ohm's law, current is related to the quotient of potential difference and resistance. And potential difference is equivalent to the induced EMF, which is equivalent to the negative change in magnetic flux. Using this visual model, we can see that the system is the falling magnet here, and the surroundings is the aluminum foil and the tube, and the aluminum foil tube and the earth. F1 pointing downwards here is the magnetic force on the loop, and F2 given here pointing upwards is the force on the magnet by the loop. And due to Newton's third law, those are equivalent. And we assume that the only forces acting on the magnet are the magnetic force from the loop and the force of gravity. This model assumes that the magnet falls with the North Pole facing downward, and we need to consider the force of gravity on the magnet. The procedure was that we marked the North Pole of the magnet, measured the mass, width, length, and inner radius of the aluminum foil tube, the mass of the magnet. We dropped the magnet through the foil tube 5 times, recording the time that the magnet dropped through the aluminum foil. We're going to computationally model the interaction in VPython using the magnetic dipole that we found from lab 3, and then compare the observational results to the computational results. The observational results from dropping the magnet through the tube was that the average time in the tube was 0.978 seconds over the 5 trials. The times are given here to the left in this table. The length of the tube was 46 centimeters with a width of 0.03 centimeters and a total radius of 0.0165 meters. The magnetic dipole from lab 3 is given by 7.91091 AM squared, and the mass of the magnet is 0.024 kilograms. Here are our initial conditions represented in our VPython code, with g being the acceleration due to gravity, and the resistivity was given as the resistivity of the aluminum foil. These are the same constants from the previous slide. Here is the code for the magnetic field and the magnetic flux using this equation to the right for the magnetic field using our dipole moment equation. It is represented here in code, and then the magnetic flux is given here by this formula represented in the code. Here's the simulation loop to simulate the magnet as it falls through the loop. The force of gravity and the magnetic force are represented here, and the net force is represented by the summation of those two. The velocity and position update formulas are given here, which are derived from Newton's second law. Based on the computational results here to the left, with the magnetic dipole moment from lab 3, the average time in the tube was 1.033 seconds, but when we dropped the magnetic dipole moment down to 7.681091, the time matched our observational results. When the magnetic dipole moment from lab 3 was used, the simulation did not predict the same time, but when we decreased that magnetic dipole moment to 7.681, the predicted time matched. These results suggest that the magnetic dipole moment found in lab 3 was not far from the actual magnetic dipole moment based on the closeness in those magnetic dipole moments. Some possible sources of error are potential contact friction between the magnet and the tube, air resistance, and potential timing inconsistencies, as well as some measurement error. What if the resistivity of the conductor were reduced as close as possibility to 0? How would the dynamics change? The resistivity is directly proportional to the resistance, and nearly zero resistivity means nearly zero resistance. Resistance is inversely proportional to current, meaning there would be extremely large current. The current is directly proportional to the magnetic force, and this means that there would be an extremely large magnetic force, and the magnet would fall with a far lesser speed and would take way more time to leave the loop. What if the holes and slots were cut into the loop? How would this affect the ring currents in our model? Holes and slots would add disruptions in the rings of the aluminum tube, and this would lead to a reduced induced current. Decreasing induced current reduces magnetic force magnitude, and this would decrease the time that the magnet is in the loop, and it would fall with much less force on it than the gravitational force. Thank you.